The pre-dawn darkness of January 17, 1945, shattered into brilliant orange flame as Hauptmann Klaus Weber's artillery battery unleashed their morning barrage toward American positions near Bastogne. For 37 seconds, the four 150mm howitzers of Artillery Regiment 26 hammered enemy lines with methodical precision, their crews working with the practiced efficiency of veterans who had survived 3 years of brutal warfare. Weber smiled grimly as the last shell screamed toward its target. In 18 months of combat, his battery had never been successfully counterattacked by enemy artillery. Today, that perfect record would end in a storm of steel that would redefine artillery warfare forever. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow, I've saved something extra special for you. What Weber could not have known as he watched his shells impact in the distance was that 60 kilometers away, a revolutionary technology was painting his exact position on a circular green screen, calculating firing solutions with mathematical precision that would have been impossible just months earlier. The age of invisible artillery was ending, and German gun crews who had dominated European battlefields through superior tactics and positioning were about to discover that Allied radar could see through darkness, weather and camouflage, to deliver retribution with terrifying accuracy. The story of how American and British forces developed counter-battery radar systems that could locate enemy artillery positions within seconds of their first shot begins not with the dramatic technological breakthroughs of 1944, but with the desperate mathematical calculations of Royal Artillery officers retreating across France in 1940, trying to understand why German artillery seemed capable of destroying British gun positions before British crews could even locate their targets. Captain Ronald Hartwell of the 25th Field Regiment had spent 4 years at Cambridge studying advanced mathematics before the war transformed his academic pursuits into matters of life and death. During the chaotic withdrawal toward Dunkirk, Hartwell found himself responsible for analyzing German artillery effectiveness using fragmentary battle reports and crater analysis data that painted a disturbing picture of enemy capabilities. German artillery units were demonstrating accuracy and response times that suggested they possessed some method of rapidly identifying British gun positions and coordinating devastating counter-battery fire. British artillery doctrine, developed during the static trench warfare of the previous war, assumed that well-positioned guns could fire multiple missions before enemy forces could organize effective responses. The Germans were proving this assumption catastrophically wrong. Hartwell's preliminary analysis revealed that German counter-battery fire typically arrived within 3 to 4 minutes of initial British artillery activity. This response time was impossibly fast for traditional sound ranging or optical observation methods, particularly given the tactical mobility that German forces demonstrated throughout their advance. The mathematical precision of German targeting suggested systematic position location capabilities that British forces did not understand and could not counter. The implications were strategically devastating. British artillery units found themselves unable to provide sustained fire support for infantry operations because each firing mission exposed gun positions to immediate retaliation. German artillery, meanwhile, could operate with apparent impunity, delivering concentrated firepower without facing effective counter-battery responses. The technological and tactical advantages that had enabled German success during the early war years extended far beyond tank design and air power coordination to include artillery systems that British forces were unprepared to confront. The foundation for Allied counter-battery radar development emerged from the unlikely collaboration between Hartwell's mathematical analysis and the electronic warfare research being conducted at the British Telecommunications Research Establishment, under the direction of Dr. Robert Watson-Watt. Watson-Watt's team had revolutionized air defense through radar technology that enabled RAF fighters to intercept German bombers with unprecedented effectiveness. The question that would drive Allied artillery development was whether similar electronic detection principles could be applied to ground-based artillery location. The technical challenges were formidable. Aircraft radar systems detected large metallic objects moving through relatively empty airspace at high speeds over long distances. Artillery detection required identifying small projectiles moving at extreme velocities through complex terrain filled with electronic interference from multiple sources. The mathematical calculations required to determine gun positions from projectile trajectories demanded computational capabilities that barely existed in 1940. Watt's initial assessment suggested that counter-battery radar was theoretically possible, but practically beyond current technological capabilities. The electronic components required for sufficient sensitivity and accuracy would be too large and complex for battlefield deployment. The power requirements would exceed mobile generation capacity. Most critically, the computational requirements for trajectory analysis would require calculation methods that could not be performed quickly enough to enable tactical responses. These limitations would have ended counter-battery radar development before it began, but for the intervention of Professor James Chadwick from Liverpool University, whose work on nuclear physics had given him insights into high-speed calculation methods that could be applied to ballistic trajectory analysis. Chadwick recognized that counter-battery radar did not require perfect accuracy to achieve tactical effectiveness. Artillery positions could be located within acceptable margins for counterfire purposes, using approximation methods that reduced computational complexity while maintaining sufficient precision. The breakthrough concept involved tracking multiple projectiles from the same artillery position and using statistical analysis to determine the most probable gun location based on trajectory convergence patterns. Individual trajectory calculations might contain significant error margins, but multiple trajectories from the same source would converge on the actual gun position with increasing accuracy. This approach transformed counter-battery radar from a precision measurement problem into a statistical probability calculation that could be performed using available computational resources. The first experimental counter-battery radar system was constructed at the Orford Ness Research Facility in Suffolk during the summer of 1941. The prototype system consisted of a modified air search radar antenna connected to analog computers that could perform basic trajectory calculations in near real time. Initial tests used British artillery firing over the North Sea to evaluate detection ranges and accuracy under controlled conditions. The results exceeded expectations. The experimental system could reliably detect artillery projectiles at ranges exceeding 15 kilometers and calculate approximate gun positions with accuracy sufficient for counter-battery fire missions. More importantly, the system could track multiple projectiles simultaneously and provide continuous updates on enemy artillery activity across extended battlefield sectors. The technology that would transform artillery warfare had moved from theoretical possibility to practical reality. Development accelerated dramatically following America's entry into the war and the establishment of joint Allied research programs that combined British electronic expertise with American industrial production capabilities. The MIT Radiation Laboratory, which had proven crucial for advancing radar technology throughout 1942, assigned its most experienced engineers to counter-battery radar development under a classified program designated Silent Thunder. American engineers solved the mobility and power requirements that had limited British prototype systems. Truck-mounted radar units with integrated power generation and computation equipment could be deployed rapidly to support field artillery operations. Improved antenna designs increased detection range while reducing the electronic signature that might reveal radar positions to enemy forces. Most importantly, American manufacturing capacity enabled production of counter-battery radar systems in quantities sufficient to support large-scale tactical deployment. The first operational counter-battery radar units arrived in North Africa during early 1943, where they underwent combat testing against German and Italian artillery positions during the Tunisia campaign. American artillery officers who had struggled with enemy counter-battery fire since the Kasserine Pass disaster finally possessed the technological advantage they needed to neutralize German artillery superiority. Lieutenant Colonel Michael Patterson of the 1st Armored Division Artillery had experienced the frustration of facing German counter-battery fire throughout the North African campaign. His battalion had lost more guns to enemy artillery than to direct tank attacks, with German forces demonstrating the same rapid response capabilities that had devastated British artillery in France. The counter-battery radar systems changed everything. Patterson's first experience with radar-directed counterfire occurred during the final assault on Tunis, when his battalion was assigned a radar team equipped with the latest SCR 584 system configured for artillery detection. Within minutes of German artillery opening fire on American infantry positions, the radar operators had identified 3 enemy battery locations and provided firing coordinates accurate enough for immediate suppression missions. The psychological impact on German artillery crews was immediate and devastating. Gun positions that had been carefully selected for concealment and protection found themselves under accurate counterfire within minutes of their first shots. German artillery units that had operated with confidence throughout the North African campaign suddenly discovered that every firing mission exposed them to overwhelming retaliation from American guns, directed by invisible electronic eyes. The tactical revolution accelerated throughout 1943, as counter-battery radar systems were deployed to support Allied operations in Sicily and Italy. German artillery commanders who had dominated European battlefields through superior positioning and coordination found themselves increasingly unable to provide sustained fire support without accepting catastrophic losses. The electronic warfare capabilities that had given Allied air forces decisive advantages over German fighters were extending to ground-based artillery operations with equally transformative effects. The full strategic implications of counter-battery radar would become apparent during the preparations for Operation Overlord, when Allied planners recognized that German artillery represented the primary threat to successful amphibious operations. The fortified positions along the Atlantic Wall included hundreds of artillery pieces, positioned to devastate landing forces during their most vulnerable moments. Counter-battery radar would provide the capability to neutralize these positions rapidly enough to enable successful beach operations. General Omar Bradley's analysis of German defensive capabilities had identified artillery as the critical factor that could determine the success or failure of the Normandy landings. German gun positions commanded every potential landing beach, with overlapping fields of fire that could destroy landing craft before troops could establish viable beachheads. Traditional counter-battery methods would be inadequate for the rapid neutralization required during amphibious operations. The solution involved deploying counter-battery radar systems aboard specialized naval vessels that could provide artillery detection and fire coordination support during the initial assault phases. These shipborne radar installations would work in coordination with land-based systems deployed immediately after beach establishment to maintain continuous counter-battery coverage throughout the campaign. The technology that had emerged from desperate mathematical calculations during the retreat to Dunkirk would prove decisive during the return to Western Europe. The transformation of artillery warfare through counter-battery radar represented more than technological advancement. It demonstrated how mathematical analysis, electronic engineering, and industrial production could be coordinated to overcome tactical disadvantages that had seemed insurmountable. The German artillery superiority that had contributed to early war victories would become a strategic liability when every gun position could be detected and destroyed within minutes of revealing its location. The stage was set for the technological confrontation that would redefine battlefield dynamics throughout the final years of the European War. German artillery units that had never faced effective counter-battery fire were about to discover that their traditional advantages had been neutralized by Allied electronic warfare capabilities they could neither detect nor understand. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. The cramped quarters of HMS Warspite's navigation room had been transformed into an impromptu mathematics laboratory, where Captain Ronald Hartwell spent 18 hours daily analyzing German artillery effectiveness, using salvaged battle reports and crater measurements that would form the theoretical foundation for the most significant advancement in artillery warfare since the invention of gunpowder. The year was 1940, and Britain stood alone against a German war machine that had demonstrated artillery capabilities far exceeding anything Allied forces could match or counter. Hartwell's mathematical background had prepared him for complex theoretical problems, but nothing in his Cambridge education had equipped him to solve tactical challenges where incorrect calculations resulted in the deaths of British soldiers, rather than failed academic examinations. The data he collected painted a disturbing picture of German artillery superiority that went far beyond superior equipment or tactical training to encompass systematic capabilities that British forces neither understood nor possessed. The German artillery units advancing across France were demonstrating response times and targeting accuracy that defied conventional military doctrine. British artillery positions that should have remained secure for extended firing missions were being located and destroyed within minutes of their first shots. The mathematical precision of German counter-battery fire suggested systematic position detection methods that British forces could not identify or replicate. Hartwell's analysis revealed patterns that challenged fundamental assumptions about artillery warfare. German counter-battery fire typically arrived between 3 and 4 minutes after British guns opened fire, regardless of weather conditions, terrain features, or tactical circumstances that should have complicated enemy observation and targeting. The consistency of these response times indicated technological capabilities that transcended traditional sound ranging or visual detection methods. The trajectory analysis of German counter-battery fire demonstrated accuracy levels that required precise knowledge of British gun positions rather than approximate location estimates. German shells consistently impacted within 50 meters of British artillery pieces, achieving destruction rates that would be impossible using area bombardment techniques. This precision suggested that German forces possessed some method of determining exact coordinates for enemy gun positions within the narrow time windows available during active combat operations. Most troubling was the apparent immunity of German artillery units to British counter-battery efforts. British sound-ranging equipment and optical observation methods proved inadequate for locating German gun positions with sufficient accuracy for effective retaliation. German artillery could deliver devastating fire against British positions while remaining essentially invisible to British detection capabilities. The tactical imbalance threatened to make sustained British artillery operations impossible. These mathematical revelations drove Hartwell to develop theoretical frameworks for electronic position detection that would eventually revolutionize artillery warfare throughout the remainder of the conflict. His calculations suggested that radio frequency detection methods might enable artillery location capabilities far exceeding traditional observation techniques. The concept required technological development that did not yet exist, but the mathematical foundations indicated that such development was theoretically possible. The transition from theoretical mathematics to practical electronic warfare development required collaboration between academic researchers and industrial engineers, who could transform abstract concepts into battlefield-ready technology. The British Telecommunications Research Establishment under Dr. Robert Watson Watt represented the most advanced electronic warfare capability available to Allied forces, having already revolutionized air defense through radar systems that enabled RAF interceptor aircraft to locate and engage German bombers with unprecedented effectiveness. Watson Watt's initial assessment of counter-battery radar possibilities was cautiously optimistic. The electronic principles that enabled aircraft detection could theoretically be applied to artillery projectile tracking, but the technical challenges were substantially more complex. Aircraft represented large metallic targets, moving through relatively empty airspace at predictable velocities over extended distances. Artillery projectiles were small objects moving at extreme speeds through complex terrain filled with electronic interference from multiple sources. The computational requirements for determining gun positions from projectile trajectories exceeded the calculation capabilities available in 1940. Real-time trajectory analysis required mathematical operations that could not be performed quickly enough using existing mechanical or electronic computation methods. The electronic components needed for sufficient detection sensitivity and accuracy would require power generation and cooling systems that could not be deployed under battlefield conditions. These technical limitations represented formidable obstacles, but they also defined the research parameters that would guide Allied electronic warfare development throughout the following years. The solution would require advances in multiple technological areas simultaneously, including electronic detection sensitivity, computational speed and accuracy, power generation efficiency, and system miniaturization for tactical mobility. The mathematical frameworks developed by Hartwell provided the theoretical foundation, but practical implementation would demand unprecedented coordination between academic research institutions and industrial manufacturing capabilities. The breakthrough that enabled practical counter-battery radar development emerged from Professor James Chadwick's recognition that perfect accuracy was not required for tactical effectiveness. Artillery positions could be located within acceptable margins for counterfire purposes, using statistical approximation methods that reduced computational complexity while maintaining sufficient precision for military applications. This insight transformed counter-battery radar from an impossible precision measurement problem into a manageable probability calculation that could be performed using available technological resources. Chadwick's approach involved tracking multiple projectiles from the same artillery position and using statistical analysis to determine the most probable gun location based on trajectory convergence patterns. Individual trajectory measurements might contain significant error margins due to atmospheric conditions, electronic interference, or computational limitations, but multiple trajectories from the same source would converge on the actual gun position, with increasing accuracy as additional data became available. The statistical methodology enabled counter-battery radar development using electronic components and computational capabilities that actually existed rather than theoretical technologies that might be developed in the future. The system accuracy would improve with extended observation periods, but initial location estimates would be available within seconds of the first detected projectile. This approach provided the rapid response capability required for tactical effectiveness, while acknowledging the technological limitations that constrained practical implementation. The first experimental counter-battery radar system constructed at Orford Ness during summer 1941 validated Chadwick's statistical approach under controlled testing conditions. The prototype system successfully detected British artillery projectiles at ranges exceeding 15 kilometers and calculated gun position estimates with accuracy sufficient for counter-battery fire missions. More importantly, the system demonstrated the ability to track multiple projectiles simultaneously and provide continuous updates on artillery activity across extended battlefield sectors. These initial results attracted attention from American research institutions that possessed the industrial capacity needed for large-scale system development and production. The MIT Radiation Laboratory had emerged as the premier Allied facility for advanced radar development, combining academic research capabilities with direct access to American manufacturing resources. The laboratory's assignment of experienced engineers to counter-battery radar development under the classified Silent Thunder program accelerated technological advancement beyond anything possible using British resources alone. American engineering contributions addressed the practical deployment challenges that limited British prototype effectiveness. Mobile radar units with integrated power generation and computational equipment could be rapidly deployed to support field artillery operations without requiring extensive infrastructure development. Improved antenna designs increased detection range and sensitivity, while reducing the electronic signatures that might reveal radar positions to enemy forces equipped with radio frequency detection capabilities. The industrial manufacturing capacity that enabled American radar production in tactically significant quantities represented a crucial advantage that distinguished Allied electronic warfare capabilities from German equivalents throughout the remainder of the conflict. German electronic warfare research had achieved theoretical advances comparable to Allied developments, but German industrial capacity was increasingly constrained by resource limitations and strategic bombing campaigns that disrupted production and research coordination. American production capabilities enabled deployment of counter-battery radar systems in sufficient quantities to support major tactical operations across multiple theater commands simultaneously. The technological advantage would be meaningless without sufficient system availability to equip artillery units operating from North Africa to the Pacific Theater. American manufacturing excellence ensured that technological breakthroughs could be translated into battlefield advantages through comprehensive system deployment. The initial combat testing of operational counter-battery radar systems during the Tunisia campaign provided validation for the theoretical frameworks developed by Hartwell and the technological implementations created by Watson Watt and American engineers. German artillery units that had dominated North African battlefields through superior positioning and coordination suddenly found themselves vulnerable to accurate counterfire directed by invisible electronic detection systems. Lieutenant Colonel Michael Patterson's experience with the first operational SCR 584 systems demonstrated the psychological impact of counter-battery radar on German artillery operations. Gun crews that had operated with confidence throughout the North African campaign discovered that every firing mission exposed them to immediate retaliation from American artillery, directed by detection capabilities they could neither understand nor counter. The technological revolution that began with mathematical calculations during the retreat to Dunkirk was transforming battlefield dynamics throughout the Mediterranean theater. The success of counter-battery radar systems in North Africa validated the collaborative research and development approach that combined British theoretical advances with American industrial implementation. The mathematical foundations established through desperate analysis of German artillery superiority had evolved into practical electronic warfare capabilities that neutralized German tactical advantages and established Allied artillery superiority that would prove decisive throughout the remainder of the European conflict. The technological transformation demonstrated that theoretical research conducted under desperate circumstances could produce practical innovations that fundamentally altered military capabilities when supported by adequate industrial resources and systematic development programs. The collaboration between academic mathematicians, electronic warfare researchers, and industrial engineers created synergistic capabilities that exceeded anything possible through individual institutional efforts. The foundation had been established for the comprehensive deployment of counter-battery radar systems that would support Allied operations throughout the Italian campaign, the Normandy invasion, and the final assault on Germany itself. The mathematical insights that emerged from British desperation during 1940 had evolved into technological capabilities that would prove decisive for Allied victory in Europe. The stage was set for the operational deployment phase that would demonstrate the full strategic implications of electronic warfare technology applied to artillery detection and counter-battery fire coordination. German artillery units that had never faced effective technological countermeasures were about to discover that their traditional tactical advantages had been neutralized through Allied innovations they could neither detect nor duplicate. The scorching heat of the Tunisian desert had become a familiar adversary for Oberst Friedrich Steiner as he supervised the positioning of his artillery regiment near El Guitar on March 23, 1943. For 18 months his experienced gun crews had dominated North African battlefields through superior tactical positioning and rapid counter-battery responses that had proven devastatingly effective against British and early American forces. The psychological confidence that came from artillery superiority had sustained German morale throughout the increasingly difficult desert campaign, but that confidence was about to be shattered by technology that Steiner could neither see nor comprehend. 6 kilometers away, Technical Sergeant Robert Mackenzie of the 1st Armored Division Artillery was calibrating the first operational SCR 584 counter-battery radar system to see combat deployment in the European theater. The 24-year-old electronics specialist from Detroit had spent 8 months mastering the complex procedures required to operate equipment that represented the most advanced electronic warfare technology available to Allied forces. Mackenzie understood that his radar system possessed capabilities that could fundamentally alter artillery warfare, but he had never experienced the satisfaction of proving that technological superiority against veteran German opponents who had never faced effective electronic countermeasures. The morning engagement that would demonstrate the revolutionary potential of counter-battery radar began with routine German artillery preparations intended to disrupt American infantry positions, preparing for the final assault on Axis defensive lines. Steiner's regiment had selected firing positions that provided excellent concealment and protection, while enabling concentrated fire against American assembly areas. The German artillery plan reflected decades of tactical doctrine emphasizing rapid displacement after firing missions to avoid enemy counter-battery responses that typically required 15 to 20 minutes for coordinate determination and fire mission execution. Steiner's confidence in his tactical approach was justified by extensive combat experience throughout the North African campaign. German artillery units had consistently outmaneuvered Allied counter-battery efforts through superior mobility and position selection that made enemy retaliation ineffective or impossible. The psychological advantage of operating with apparent impunity had enabled German artillery to provide sustained fire support that compensated for increasing material disadvantages in other areas of military capability. The first indication that conventional artillery warfare had been revolutionized came at precisely 0547 hours, when Steiner's lead battery opened fire against American positions with a carefully planned barrage intended to suppress enemy defensive preparations. Within 18 seconds of the first German projectile leaving its gun tube, Mackenzie's radar system had detected the incoming rounds and calculated preliminary firing coordinates for the German battery location. The mathematical precision that had required months of development was functioning exactly as theoretical models had predicted. Mackenzie's training had emphasized the critical importance of rapid response procedures that could deliver counter-battery fire before German units could displace to alternate positions. The tactical window for effective retaliation measured in minutes rather than hours, requiring coordination between radar operators, fire direction personnel, and gun crews that exceeded anything previously demanded in artillery operations. The technological advantage provided by electronic detection would be meaningless without execution capabilities that could capitalize on the information being provided. The first American counter-battery mission, directed by radar-derived coordinates, landed among Steiner's guns at 0551 hours, just 4 minutes after the German barrage had commenced. The accuracy was devastating and unprecedented. American artillery shells impacted within 20 meters of German gun positions that had been carefully selected for concealment and protection against conventional detection methods. 2 German howitzers were destroyed immediately, and the remaining guns were forced to cease fire and seek alternative positions under direct artillery attack. The psychological impact on German artillery crews exceeded the material damage inflicted by American counterfire. Veteran soldiers who had operated with confidence throughout 18 months of desert warfare suddenly discovered that their tactical expertise and positional advantages had been neutralized by invisible Allied capabilities they could not identify or counter. The fundamental assumption that well-positioned artillery could fire multiple missions before facing effective retaliation had been proven catastrophically wrong. Steiner's immediate response reflected the tactical flexibility that had enabled German artillery success throughout the North African campaign. His remaining guns displaced rapidly to alternate positions that provided similar fire support capabilities, while offering different approaches for concealment and protection. The established German doctrine emphasized multiple prepared positions that could maintain fire mission effectiveness while complicating enemy counter-battery efforts through unpredictable location changes. The second German fire mission commenced at 0612 hours, from positions located 3 kilometers from the original battery location. Steiner's tactical analysis suggested that American counter-battery capabilities, however sophisticated, would require extended observation periods to locate the new firing positions. The rapid displacement had provided sufficient tactical separation to restore German artillery effectiveness, while forcing American forces to repeat whatever detection processes had enabled their initial successful retaliation. Mackenzie's radar system detected the second German fire mission within 12 seconds, and calculated new coordinates that reflected the battery displacement with mathematical precision that German tactical doctrine had not anticipated. The technological capabilities that enabled counter-battery radar exceeded traditional military assumptions about detection and response timeframes. Electronic position determination was not constrained by the geographical limitations that governed conventional observation methods, or the time requirements that enabled tactical displacement between firing missions. The American counter-battery response against Steiner's second position arrived at 0615 hours, with accuracy that eliminated any remaining doubt about Allied electronic warfare capabilities. German artillery positions that should have been secure from detection were being located and engaged with precision that made sustained fire mission execution impossible. The tactical principles that had governed artillery warfare throughout military history had been fundamentally altered by technological developments that German forces could neither replicate nor counter. The transformation of artillery warfare through electronic detection created psychological pressures that extended far beyond immediate tactical considerations. German artillery crews who had dominated battlefields through superior training and tactical doctrine discovered that their expertise had been neutralized by Allied technological advantages they could not understand or overcome. The confidence that enabled aggressive artillery operations was being replaced by uncertainty and vulnerability that undermined fundamental military effectiveness. Steiner's tactical assessment of the morning engagement revealed the strategic implications of Allied counter-battery radar capabilities. German artillery units could no longer provide sustained fire support without accepting prohibitive losses that would eliminate their tactical effectiveness within hours rather than days. The mathematical precision of Allied counterfire suggested systematic detection capabilities that rendered traditional artillery displacement and concealment techniques ineffective. The immediate tactical response required complete revision of German artillery doctrine to accommodate Allied electronic warfare advantages that had not existed during previous campaigns. Fire missions would need to be limited to single volleys, followed by immediate displacement to positions located far enough from original sites to complicate electronic tracking. The sustained fire supports that had proven crucial for German tactical success would no longer be possible against opponents equipped with counter-battery radar systems. The strategic implications extended throughout German defensive planning for the remainder of the North African campaign and beyond. Artillery superiority had provided crucial advantages that compensated for increasing Allied material superiority in other areas of military capability. The neutralization of German artillery effectiveness through electronic warfare would require fundamental changes in tactical doctrine that might not be achievable given existing resource limitations and training constraints. Mackenzie's successful demonstration of operational counter-battery radar capabilities validated years of theoretical research and technological development that had transformed academic mathematics into practical military advantage. The electronic warfare capabilities that began with desperate British analysis during the retreat to Dunkirk had evolved into technological systems that provided decisive tactical superiority against veteran German opponents who possessed no equivalent capabilities. The psychological transformation was as significant as the tactical revolution. American artillery units that had struggled against German counter-battery fire throughout the early North African campaign suddenly possessed technological advantages that enabled them to dominate artillery duels against experienced opponents. The confidence that came from technological superiority created positive feedback effects that enhanced overall military effectiveness beyond the direct capabilities provided by radar systems themselves. The success in Tunisia established counter-battery radar as an essential component of Allied artillery operations that would be expanded and refined throughout subsequent campaigns in Sicily, Italy, and northwestern Europe. The technological advantage demonstrated against German forces would be systematically exploited through comprehensive system deployment and tactical doctrine development that maximized the strategic potential of electronic warfare capabilities. The operational validation of counter-battery radar technology demonstrated the practical value of sustained research and development programs that could transform theoretical concepts into battlefield advantages. The collaboration between academic researchers, industrial engineers, and military personnel had produced innovations that fundamentally altered military capabilities through systematic application of scientific principles to tactical problems. The German artillery units that had never faced effective technological countermeasures were beginning to understand that their traditional advantages had been neutralized through Allied innovations that represented a new form of warfare they were unprepared to confront. The electronic dominance that would characterize Allied operations throughout the remainder of the European conflict had been established through technological superiority that German forces could neither match nor counter effectively. The foundation had been established for comprehensive deployment of counter-battery radar systems that would support Allied operations throughout Italy and the preparation for Operation Overlord. The psychological impact on German forces who discovered that their artillery could no longer operate with impunity would influence tactical planning and operational confidence throughout the remainder of the conflict. The revolution in artillery warfare that began with mathematical analysis had achieved practical validation that would transform military operations across all theaters of Allied engagement. The technological advantage gained through years of systematic research and development had proven its value under combat conditions that validated theoretical predictions and justified continued investment in electronic warfare capabilities that would prove decisive for Allied victory in Europe. The humid Mediterranean air carried the acrid smell of cordite and electronic ozone, as Major William Harrison supervised the installation of the latest AN/MPQ-4 counter-battery radar system at the staging area near Gela, Sicily, on July 15, 1943. The technological sophistication represented by the new equipment exceeded anything Harrison had encountered during his previous engineering assignments, yet the system's operational requirements demanded field deployment under combat conditions that would test both equipment reliability and operator competence. The success achieved in Tunisia had validated the fundamental concepts underlying counter-battery radar technology, but the upcoming Italian campaign would require enhanced capabilities that could function effectively against German defensive preparations that had been specifically designed to counter Allied electronic warfare advantages. Harrison's background in electrical engineering at MIT had prepared him for complex technical challenges, but the practical requirements of deploying sophisticated electronic equipment under combat conditions demanded innovations that transcended traditional engineering approaches. The counter-battery radar systems required precise calibration procedures that could be performed rapidly under battlefield conditions, while maintaining accuracy standards that enabled effective artillery coordination. The technological complexity that provided decisive tactical advantages also created vulnerability points that could compromise operational effectiveness if not properly addressed through systematic engineering refinement. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.